All right. What we're going to do in this hopefully relatively short screencast is talk about the force of friction in a little bit of detail. Okay. The force of friction is a force, we're talking about surface friction here. Force that happens between two surfaces when one either slides across the other surface or tries to slide. When you're actually sliding across the surface, so the surfaces are moving relative to each other, that's called kinetic friction. And when you're pushing something and it's stuck, the surfaces are stuck together, but they wouldn't be if there was no stickiness, that's called static friction. Now, both friction forces depend on two factors. One, they depend on how hard the two surfaces are pushed together, and that would be measured by the normal force. The bigger the normal force, the bigger the force pushing between the two surfaces. And also this thing called coefficient of friction. In the case of kinetic friction, it's a value that basically tells you how sticky any two surfaces are. So basically, it gives you coefficients of friction in this table for different materials. So steel on steel, the static friction coefficient is slightly bigger than the kinetic coefficient because, as we discussed in class, it's a little easier to slide something over a surface than to break the stickiness. And these values are always somewhere between 0 and 1, almost always. And you can see that each two materials are going to have a different amount of stickiness between them. And the higher the number, the harder, the more friction they have. Okay? So we can go and look at that table. But basically, if you were to calculate the kinetic friction force, it doesn't matter how fast you're moving one surface over the other. All that matters is how hard the surfaces are pushed together and what the coefficient of friction between the two surfaces is. And that will always tell you how much kinetic friction you have between any two surfaces. Okay? So if we were to draw, let's say we do this. We have an object that's sitting on a table, and it's like pulling on a crate with a rope tilted upwards. And you can see, here's a free body diagram. I've got a downward weight force, an upward angled applied force, which can be broken into a horizontal and a vertical component, and a normal force that is there to keep the thing from falling through the floor. If this force was too big, and this applied upward force is bigger than mg, then this would come right off the surface. But assuming that it doesn't, this force is less than this force, and the difference is made up by the normal force, so vertically the whole thing's in equilibrium. It doesn't accelerate up or down. But if I include friction in this scenario, then I would have a countering force to the forward pushing force. So the vertical forces all cancel. The horizontal forces are imbalanced, presumably. I mean, they don't have to be. You could be moving, and these two forces are equal, so you'd be moving at a constant velocity. But in this example, the applied force component in the x direction is bigger than the kinetic friction force, so your net force horizontally would be this component minus that friction force, and that would equal ma. And this is just, if we were to map out the y forces, we would get that this force equals this force minus that force. That would make them all balance. Really, n plus f applied sine theta equals mg. This plus this must balance that. But in the x direction, you basically, the F net is the applied force to the right minus the friction force to the left. The applied force to the right is F applied cosine theta, that's this component, minus the coefficient of friction times the normal force. So now I got to figure out what the normal force is, so I did that above, because in order to determine the amount of friction force, I got to multiply the coefficient times the normal force, and I need the vertical setup to determine what that normal force is. So once I do that, I now have the complete equation. So if I know what the applied force is and what the angle is and the coefficient and the mass, then I can figure out what the acceleration would be under these situations. But basically, for now, because we're going to do a lot of examples like this with looking at free body diagrams and tallying up the forces, for now, we know the kinetic friction force is the product of the stickiness coefficient or the coefficient of kinetic friction and the normal force. Now, static friction is something a little different in that it is a resistance to motion, but it's really a resistance to potential motion. So if I apply a small force to this, the static friction force will equal my pushing force to keep it from moving. And if I increase this pushing force, if I still have enough static friction, maximum static friction to hold, I will just increase this amount of static friction force to the maximum value. Once I exceed the maximum possible value that static friction can exert, then I start sliding and I go into kinetic friction. You break free, you start sliding. The kinetic friction force is always a little bit less than the maximum static friction force, as you can see from this graph. So basically, in the graph, what this says is this is basically, let me see if I go back here, it's like this. I'm looking at a graph of the applied force on the x-axis and the static friction force on the y. I'm not saying physically on the x and y axis, but I make a graph of this amount of force versus that amount of force. So I'm going to keep increasing this force and see what it does to this force. And so what I see is when I'm in the static region, there's a one-to-one relation. If I increase the static friction force, if I increase this is F right here. If I increase the force, the pushing or applied force by 1 unit, I increase the static friction force by 1 unit. If I increase it another unit, I increase the static friction force another unit. And that will keep happening until I get to the point where this is my maximum possible static friction force. If I push a little bit harder, it's going to start sliding. And then I drop a little bit because it's a little easier to slide than to unstick it. And I get a constant kinetic friction force, as we just discussed, equal to the coefficient of kinetic friction times the normal force. So the static friction force is going to be greater than 0 and less than or equal to the maximum static friction that you can have. And that equals, similar to the kinetic friction, it's the coefficient of static friction times the normal force. So if you're right at the boundary of breaking static friction, the amount of max static friction you can have is this value right here. Okay? And yes, the static friction coefficient for the same two materials is always a little bigger than the kinetic because it's a little easier to unstick, to slide something than to get it unstuck. Okay? So here's someone pushing on a refrigerator. He pushes a little bit. The applied force is equal to the static friction force, which is less than the maximum static friction force, which is mu s times the normal force. He pushes a little harder, not hard enough. The static friction force can still meet this force. This is the maximum static friction force, because right a little bit more it's going to slide, and that equals mu s times the normal force. That equals that amount. And then finally, you have applied enough force to break the static friction, and you're sliding, and if your applied force is going to be bigger than your kinetic friction force, at least at first, if you have maintain the force it took to break the static, and so you will have a forward acceleration. And so F applied minus Fk will equal ma. And if you wanted to just move this at a constant velocity, you could just drop this down, so your applied force was now equal to your kinetic force, and you could keep moving at a constant velocity from that point on. Okay, so let's ask a couple of questions here, and that will wrap up our introduction to friction force. So what if you press a book flat against a vertical wall with your hand? What direction is the friction force exerted by the wall in the book? Okay, first of all, if it's stuck, it's going to be static, and if it's sliding down the wall, it will be kinetic. But in either case, what direction does the book want to slide? It wants to slide down, and therefore the friction force is going to be directed straight up. The friction force is always parallel to the boundary between the two surfaces, so it will be upward. if you're on a crate sitting on a flatbed truck, the truck accelerates, the crate moves with it. It's not slipping. In what direction is the friction force exerted by the bed of the truck on the crate? The truck's moving to the east. And then this is kind of interesting because it's not sliding. It is accelerating with the truck, but there's no sliding between the surfaces, which means if there was no friction, the truck would slide out from underneath the crate, but it doesn't because it grabs the crate and pulls it. That's actually a static friction force. And since the crate is accelerating with the truck, that static friction force must be in the same direction that the truck is accelerating, and that is to the east. So think about that. And then finally, your friend's on a sled. You want to apply a force on your friend, either upward or downward. So you have the same force. You're going to get the same horizontal component of force. Is it easier if you do it A or do it B? Think about it. Okay, I vote for B. And I want you guys to think about why that's true. I won't say it in the screencast. Why is it easier to slide the person in situation B rather than situation A? Okay, so that wraps up this screencast on friction. So listen to it, and let me see. I've got to. You can ignore what I say from here on. I just have to go back to QuickTime and stop the screencast. Okay, file. New screen recording. All right. Uh-oh. Uh-oh. Okay. Oh my God. I didn't record it.